In this example, I have this 1000 Newton force that acts in the direction from A to B. And what I want to do is determine the moment that this force produces about point C. If we assume that the force acts at point A, and then we do it again if we assume it acts at point B, and we do it again if we assume it acts at point D. Now, what we should see is as long as we move this force along its line of action, it should have no noticeable effect. The moment that we have at all these points is going to be exactly the same. Now, the first thing I need to do is I need to break up this 1000 Newton force into its x and y components. So when we do that, let's look at this. I'm calling this angle right in here theta. And my 1000 Newton force, it's going to the left and down. So I'm going to have two components, one that points to the left, one that points down. This one is going to be 1000, and that's going to be times the sine of theta. This is going to be 1000 times the cosine of alpha, this alpha value. Now, alpha, we can calculate. Alpha is going to be this inverse tangent of 42 over 144. 42 is the opposite side of this triangle. 44 is the adjacent side. So from SOHCAHTOA, we can say this is going to be the inverse tangent of 42 over 144. Now we can do that calculation. And we get that this is equal to 16.26 degrees. So this will be 1000 times the sine of 16.26. This will be 1000 times the cosine of 16.26. And let's actually figure this out. So 1000 times the sine of 16.26, 279.99. So we'll call that 280. And if we do the cosine, (960.00), so this will be called 960 newtons in newtons. Now, the nice thing about this is we figured out, let's say this was at point A, but if we look at point B and point C, they're all on its line of action. So if we had a vertical line at each of those points, this angle inside is going to be alpha. So that means that when we break up the components, all the components are going to be the same at all of these different points anyway. So we don't need to do anything else. And we don't need to break up the components for each of these steps. It's going to be the same component, granted that it's the same because it's the same angle. Okay, so now let's look at point A. And at point A, I'm going to have this 280. And then I'm looking at point C, which is down here. And I'm also going to have this force. They're in line with each other. I didn't draw it amazingly, but they're in line with each other. So this 960 Newton force is in line with C. Now, the only dimension I know is from A to C. This entire length right here is going to be 200 millimeters, or 0.2 meters. Okay, so when we look at the moment about D, let's rotate my problem counterclockwise, and I'm going to have 280 times this perpendicular distance of 0.2. I know 280 is positive because when I rotate, if I pin my problem at point C and I rotate the entire problem, assuming C is what I'm rotating it about, then my this is going to rotate like this. Because it's rotating, and it's rotating head first, the vector's rotating head first, we know it's positive. Now with 960 goes right through point C. So there is no perpendicular distance. If you want it to be complete, you could say this is 960 times 0, but that's just going to go away and that's going to be 0. So we know that this moment is going to be 280 times 0.2 or 56 in my units. This is a Newton, this is a meter, so I have Newton meters. All right, now let's look at point B, and we should get the exact same answer. Okay, so point B, here's B, here's C. These are my distances, so this is 42 millimeters or 0.042 meters. This is 0.056 meters. Okay, and then we have this force, that's 280. We have this force that is 960. So now we're just going to do the exact same thing. We're going to rotate counterclockwise. We're going to say the moment at D is going to be equal to what? Well, as we rotate about point C, if we pin our problem at point C and rotate this way, we see that, well, the 280, this one's more difficult. So what we can actually do is we can say, all right, this is the line of action of the 280. We can move it back so it's closer to this 2 point C, so it's perpendicular to it. So nothing changes. We're still moving it along its line of action. And now it's easier to see if I'm rotating it counterclockwise, it's going to rotate head first. So it's going to be positive again. So it's going to be 280 times its perpendicular distance, which is this. So this 0.056. And then the 960, well, this one's easier to see just because of how I've drawn it. But when we rotate it, it's also going to rotate around point C in head first. So it's going to be positive. So it's going to be plus 960 times its perpendicular distance, which is this 0.042. So now when we put this in the calculator, we should get the exact same answer. And we get it. We do. We get this is equal to 56 Newton meters. All right. So now let's look at point D. I know my scroll bar says C, but this is point D. So point D is directly horizontal to point C, but it's some distance D. Okay. Well, a little bit of trig. We have similar triangles. So we have this big triangle right here, and we can say D over 56 plus 144. So this side over this side is going to be equal to this side, so 42 over 144. So D will be equal to 42 times 200 divided by 144, and this will be equal to a distance of 600 millimeters, or 0.6 meters. Let me just make sure I did that right. So I actually had a typo over here. So it's 42 times 200 divided by 144. So it's actually 58.3 millimeters. This that 600 just seemed way too big as I was doing this. So this is 58.3 millimeters, which seems a lot more reasonable. Okay, so we know this distance is 0.0583 meters. When we draw our forces, this will be 280. This will be 960. Well, what do we know? When we sum the forces for D, this will be 280 times 0, it goes through point C, so there's no perpendicular distance. And then when we rotate, we see that 960 goes head first. So it's going to be 960 times 0.0583. So we'll multiply this distance by 960, and we get, yes, this is also equal to 56 Newton meters. So there you go. This example shows you that it doesn't matter where we move this along its line of action. The force, as long as we get our distances right, will always exert the same moment on a point.